information. So the idea of the second part is going into more detail on how we develop models, quantitative models, and the basic rules of doing those models. As you will see, there is a very direct relationship between the structure that we see in causal loop diagrams and the structure in stock and flow diagrams. And the structure that you see in causal loop in stock and flow diagrams. However, as you become more experienced with SD, and that's somehow happened to me, is that I tend to go straight into stock and flow diagrams once I become experienced, because somehow that helped me to look directly into the accumulations that are happening in the system. Because the causal loop diagram sometimes is not quite precise in that sense. You may need to think a little bit more careful of, is this variable an accumulation? Is this variable something that accumulates into that accumulation? So sometimes going straight into a stock and flow diagram, even without any data, can be a little bit more precise than a causal loop diagram. So this is part of the basic structure, and the other thing about stock and flow diagrams is that basically we go directly from the stock and flow diagram to the model. So we start working directly on the software and having the almost a model ready to run. So stocks and flow basically is the dynamic aspect of the system. It's what tells you or what shows you the trajectory of the variable. You can see the variables accumulating or decreasing or being stable over time. So that's why I usually associate the stock and flow to the dynamic aspects of system dynamics. Basically, there are accumulations that define the state of the system. So you can use a stock to represent a person. For example, we are stocks of feelings. We are a stock of knowledge. We are a stock of calories. You can take an even a definition of a stock at the almost much higher level, which is we can be a stock of population if we want to see the number of people on a certain age or a certain gender. We can even be a stock of air, right? There are very interesting models capturing the atmosphere and the gases in the atmosphere. So that's concept of stocks is very flexible, but it's also very powerful because accumulations tends to have inertia, and it tends to be the source of the information that we see when people make decisions. If you put into, for example, if you are considering yourself as a stock of calories, you will measure your accumulation in terms of kilograms. Based on what the scale tells you, you may stop eating or you will do more exercise. So somehow the scale, which is the measure of the accumulation of calories in your body, right? The scale is the measure, but really the accumulation is what you have in terms of weight in your body, determines what you are going to do next in terms of how much are you going to eat or how much exercise do you engage with. The same happens with other systems. If you are thinking in population, the memory of the different birth and death rates is the number of people that live in a certain place, right? The memory of the system of all these actions that are captured in the flows are the accumulation, the final numbers that you have in terms of populations. And based on that, it tends to be used for calculations. They tend to be used to define policies. So that stocks are clearly the source of information. Stocks can be tangible, so something that you see or something that you don't see, right? Belief, perceptions. So it's a very, very flexible concept. So basically, the way that we represent the stocks, we say that stocks can be, if you need to explain somebody what is a stock, you can use the bathtub analogy, where you say the stock is a bath and the accumulation is the water that is filling from the tap, and the tap is the flow. You don't see, well, you see a line of water coming in, but what you really see is the line of water accumulating here. And if you open the drain, the waters will flow out. So that is something that you can use to explain somebody that. In Vensim, you already see this structure, right? The stocks are usually the boxes or level. They call it level in Vensim. But you start drawing a box, right? A level of population, and then you draw the flow, right? The rate, which is the process that leads to that accumulation, in this case, the birth rate, or you can draw the outflows from that stock, the death rate, right? You draw from outside. But basically, and that's why somehow Vensim is or the software in system dynamics is quite simple or easy to manage, is that as you are drawing these boxes and this flow, the software, any software that you use in system dynamics is automatically creating the equation, the integral equation for that stock and flow. So they will automatically say that population is equal to the integral of the birth rate minus the death rate multiplied by the delta time, the dt, plus what was the stock, the initial value of the stock. So basically, when you are entering that equation, you are writing this. When they ask you in Vensim what is the initial value of the stock, is basically you are providing this information, the stock at T0 at the start of your simulation. And then the software continuously do, if you have an inflow, they add the inflow and they subtract the outflow. And that is basically how the software works. The interesting thing, and that's why I said that there is parallels, is that with the stocks and flow, you can see reinforcing feedback process, right? With the stock and flow, you will see the accumulation, that line that is growing exponentially over time, depending if there is a reinforcing feedback process. And you did that in the exercise. So bank account, in this case, is the accumulation, the state of the system, that tends to be increased by the income that is generated. And how this income is generated is basically from the amount of money that you have in your bank account multiplied by an interest rate. So there are always a factor, right, that multiplied by the stock will give you a certain response, that then that response, it can go elsewhere or it can come back to the stock, right? We can, this structure, this reinforcing structure can be associated almost to any process that you see that there is an exponential growth. Can be a bank account, can be population with the birth rate, can be the number of people with COVID, right? This is the number of people infected. The famous R is the number of people that have the disease, and then you keep accumulating. So basically, any exponential growth structure tends to follow the same structure. So any exponential growth tends to have the same structure, and that's why it tends to be quite flexible, quite simple in terms of model, because that structure tends to repeat over and over. So you will see most of the time two types of structure: exponential growth or balancing processes. And is basically the stock multiplied by a certain variable, that accumulate through a flow, and you see that repeating over and over time. Exponential growth, but the interesting thing, rather than just simply looking at doing the model, is to understand what we see in terms of these dynamics. And one thing is very important here is that the accumulations tends to create the inertia in the system. As they say, it's the memory of the system. So the bank accounts tends to see what you can measure at the end of every month. What you cannot measure is how much interest you are earning every day. So when you are thinking in terms of measurement and data sets, you will always have or most of the time you will have the information about what is happening in the stock, but very rarely you will have the information of the flow. However, sometimes you have the information of the flow, and if you have the information of the flow, you may infer what is happening to the stock. So if you see that there is a net flow which is positive, right, you will see that you can infer that the trend for this stock will be growing over time. So, and vice versa. So if you have clear this understanding of what is an accumulation in one variable and what is a process in another variable, you can immediately start seeing how you may infer the dynamics of the system based at least on these pieces of information. Exponential growth arises from positive feedback process. One interesting thing about exponential growth is that double time is constant, and this is very, very interesting. If the state of the system is growing at the same rate, so if you have the same percentage of interest rate, it will take the same amount of time of growing from 1 million to 2 millions that growing from 2 millions to 4 millions. But the implications are completely different, right? If you are thinking in terms of an epidemic, it takes you the same time from moving, for example, from 50,000 to 100,000. If the rate of contagion is the same, it will take exactly the same amount of time of moving from 100,000 to 200,000 people with the disease. But the implications are completely different. So that's why sometimes you need this type of model to see mostly the scale that you are facing in terms of the system. So the state of the system double in a fixed period of time, no matter how large. If that rule, if this percentage of growth remains the same, it will take the same amount of time to double huge size of the system. And this was very interesting capture in a model by Jay Forrester. Jay Forrester is the founder of System Dynamics, and you see that one of the readings from John Moorcroft is about Jay Forrester. And he created in 1971, precisely 50 years ago, a model of the world, what's called world dynamics. And that model is very, very simple. It's almost a masterpiece on capturing something so complex as the society, as the world that we live in. And in that model, it clearly says that if population is growing at the same rate, it will take the same amount of time of moving from 2 billions to 4 billions, from 4 billions to 8 billions, from 8 billions we are now to 16 billion people. But imagine the implications of that growth in terms of natural resources consumption, in terms of pollution created, and all these consequences. And this is something that he captured in that model, is that sometimes exponential growth, when it's not constrained somehow, it can have very important implications for the rest of the system. So the net increase rate depends on the size of the state of the system. I don't know what is doing that. But let's see something that is more contemporary. And here I'm going to stop for a moment for you to do your initial model. the initial practice model, and we will do a simple model, right, of Facebook. So let's and this is a very simple model. You can see that Facebook, in terms of growth over time, they started in 2004 with almost no users. 2007 may have approximately 50 million users. 2008 maybe 150 million users. 2009 almost 370 millions. 2010 almost 670 millions, and 2011 almost 900 million users. If you see in 3 years from 150 millions to 900 millions, that's huge. That growth is huge. So that is a clear example of exponential growth, and this is what's happening with many of the social media websites and anything that is not constrained by scale in terms of the growth. Like most of the internet-based companies, they are not constrained by scale, unless they do a very bad job in terms of website. But we can do a small model for that. So I'm going to stop here. What is happening? And let's try to do. Let's take 10 minutes. Try to do that that model, that basic Facebook model. I can show you the screen if you want of the model. And let's try to calibrate. Let's see if we can get that growth over time. And there are two interesting implications. One is if you are trying to calibrate that time series, that you try to understand what is happening with that growth, is we need to find out what is that rate of growth. So that created interesting implications in terms of how you create that model. So let's take 10 minutes, have that structure there. I'm going to and then we can I will ask any volunteer to show the structure and to see what how you did it and what you get in terms of the results. Let me know if you want to see the structure again, or you want to start on your own for that structure. No, let's do the following. Sorry, I will share my desktop. So here you have the structure. Okay. Oops. So I hope you can see my screen with the structure, right? So you have Facebook. And you have a stock of adopters of Facebook, right? And you have one flow, which is the adoption rate of the number of people that are starting to use Facebook, right? And we can start that after you and you see that in terms of the model. Adopters is the number of people that somebody raise your hand. Yes. Any questions? Sorry. Sharif, do you have a question? Or that was a legacy hand?
Sorry, it's a legacy hand, I think. Sorry,
okay.
I haven't got a chat function this time, so I can't type.
Okay. So there is a question from Frederick. The stock can be both tangible. How can you calculate the accumulation of an intangible stock? That's a very good question. Intangible stocks are usually a bit difficult to calculate, you tend to use proxy variables. For example, if you want to know the number of skills of a person, maybe you can, and this is an intangible stock, maybe you can calculate through a proxy, for example, the number of languages that they speak, if you want to measure the skill of being able to speak different languages. Or you can measure in terms of, for example, a number of words that they can type. If you want to measure the skills in terms of typing, a different typing. You can measure another intangible, for example, when you say reputation. Well, you don't have the ability to measure completely that, but you can measure, for example, in terms of positive comments that somebody leave in TripAdvisor. So if you see that over a period of time, if people are increasingly making positive comment in TripAdvisor, that's a way of approximating what is the accumulation of a good reputation for a company. So for some variables, you need to use proxy variables in order to measure that. So yes, it's usually a bit of a complex intangible stocks, but they are always a challenge, an interesting challenge when you are doing these models, especially this type of variables. So basically in this structure, we have adopters, and we have here this variable that we call adoption from word of mouth. That's almost a behavioral variable, right? It's a variable that tries to put in only one concept the process of somebody telling somebody else that likes Facebook. So basically, you see that adoption from word of mouth, you need adopters, right? You need people who can talk about Facebook. You need as well that people can talk with other people, and that is the contact rate, right? So you have a certain contact rate, the number of contacts. If we are thinking on this same structure for the epidemic, the contact rate will be the number of opportunities that people talk with each other, or they met in certain aspects. And the final one is the adoption fraction. It's really that contact may not generate a new Facebook user. So there is some potential chance that contact may not generate that adopter. It's like an epidemic. Maybe that contact does not infect the other people. And these are three concepts. And this structure tends to be present in business, as I said, from new products. Tends to be present in for example, in goodwill, in terms of organizational process, in epidemics. So it tends to be a very, very sort of a well-standard structure in SD. Would anybody can share the screen? How are you progressing with this initial model? You can see Kim writing. Kim. If you want to share the screen, let me know or raise your hand. Yes, Usame, you use the arrow going to adoption rate. Has that arrow, what do you think it has that arrow from adoption from word of mouth? It will be a positive or negative? Anybody wants to share the screen? Exactly, positive. That's right, Usame. Nobody wants to do it. Yes, that's and that's why I wanted somebody to share the screen. Is that
So
yes?
I
What
can
numbers
share
do
my
we have
screen
to
if
put?
you want to, Martin.
Okay, perfect, Moritz. Yes, please.
I just have to
I will
figure
stop
out.
sharing my screen. Yes.
So I'm not 100% done yet.
No, that's fine. That's fine.
So this is how it looks like at the moment, right?
That's fine. Yes. Do you have all the equations there?
No, I have the equation here for
Okay.
the adaptation.
Yes, that's good. Yeah, that's okay. You can press OK on that one.
So
yes. So yes. So somehow let's go through the process. So we have the structure here. We say that we see the time series of Facebook, and we agree that this is growing exponentially, and there is this behavior process that adopters talk with people and then try to influence. So if we go to the stock of adopters, that's the question that Nina has. What numbers do we have to put as value? So it depends where do we want to start our simulation. Do we want to start from 2004, or do we want to start from 2007? And that's why it's important the time horizon, right? So let's suppose that we start in 2007, and this is 50 million to start. That's an approximation, right? So perfect. That's the initial value for the accumulation, right? We start with an accumulation of 50 million, so we can say, okay. So then at adoption rate, it will be just simply the variable that is coming into, right? The adoption from word of mouth. Yeah, you can choose from the variable that you have in the box there.
Here?
You don't need to type. No, go to the right, that box. No, down.
This
down
one.
To the right.
Yeah, okay. Yeah,
yeah,
that's
that
easier.
one. Yeah, exactly.
Yeah.
Yes, yes, save it. So you see, another of the reason why we pay a lot of attention on drawing the structure before we write the equation is because you need that in order for your equations. Otherwise, it's you need to type everything. But if you have those variables there, you just simply choose the variable and use the mathematical operator, and that's it. Perfect. So the adoption fraction here, what we don't have is a specific number. So to reduce the process of search of what can be a sort of the number, that is usually quite a daunting task. Until you can sort of refine it. That number. I will give you sort of a hint for that value. Let's just start with a value of, just give me 1 second. There is a question, does the plus or minus affect No, it's mostly for us when we are looking at the at the graph, understanding a bit more of what is that graph. Let's suppose that the adoption fraction is 5%, right? That will be 0.05. Right? So we say that for every contact between an adopter and a contact rate, there is a 5% chance that they become an adopter. And the contact rate, we can start with something like, it depends on the number of how many friends do they have. Let's suppose that you have 20 friends, right? Everybody has 20 friends that they show that they have that they are using Facebook. So you see that we have all the data, at least the initial data for this. So now we can run our first experiment and see really how we are doing. So if we run simulation, yes. Okay, why is that? Perhaps you need to save it. No, save it in your own computer. Yes, please. Yeah, I will explain a little bit more why we need at least to have plus or minus. Yeah. So okay, that's run. So if you click in adopter and the graph, we can see how we got there. Okay, have you clicked in the graph? Yeah. No.
Can you see it?
No, we cannot see it. Perhaps it's because you are sharing the Vensim and the desktop.
So I probably need to share the whole desktop, right?
Yes.
So let's try this again. Here's the graph.
That's the graph. Right, we can see that perhaps this number is, well, first we don't want to run it for 100 months. This rate, and here are some of the basic debugging aspects of the modeling process. So if this is 100 months, right, what we are assuming is that every adopter talks to 20 friends every month, and from that contact, they have 5% success rate. So that means that really will explode, like we see here. You have 8 to the power of 37 adopter after 100 months. So first important issue when we are doing all the parametrization of the model, let's close this for a moment, is that, okay, is this adoption fraction based on what time horizon? Is this per year? Is this per month? Is this contact rate per year or per month? So if we go to the model, and that is something that perhaps we can, if you go to model, to the
up here.
Yes.
Yeah.
Settings.
Yes.
So here are the other parts of the integral equation. First is the initial time and the final time. We can simply simulate for example, 5 years, right? If we are assuming, we can even write something like, we say 2007 to 2020. We can write that. So we can use any number here, because for Vensim, and then the time step is that the dt that is used for the integral. If you have a dt too large, that's almost become a discrete type of simulation, and we want to make it continuously. So therefore, the time step, let's always choose a small number. So you can use 0.0625. That will be suitable for this. So, and with that, we have defined a boundary where we want to see the simulation and see if we really can calibrate and see that the behavior of the system within that time frame makes sense. So let's say, okay. And then let's run again. Simulate. Yeah.
I don't know what this keeps
Because you have that model open in with the with
over the OneDrive.
With OneDrive,
right?
Perhaps if you save it in your hard drive, that you will stop having those problems. But have you run the simulation? Yes.
Yes.
Okay. Wow. Why is that? Ooh. Okay. So let's close it. I think that is a problem with the time model. It's settings from 2007. Active initial.
Moritz, did you press the green arrow for play simulation again?
Yes, I did.
Oh, okay. Sorry.
Yeah.
Let's start with 2007.
So this should not. Is this correct or is this incorrect?
Yes, that can be another thing. Just press cancel. So if you go to control panel,
where's that?
That's to the right, to the extreme right, the icon.
This one.
Yes, click there. And data sets. That is another trick. Is sometimes you remove the first data set. So is yes, the one at the bottom.
This one.
Yes, just move it outside. So press the arrow to the left.
Left arrow.
Yeah.
So sometimes what you can do is that you run many experiments and then the graph become a little bit wrong. That's it. Yeah, you were right.
So the graph was there, but we just couldn't see it because the other one was dominating it, right?
Yeah, exactly. So many times you run the first simulation and you start accumulating different runs. When you see runs that they don't make sense, you can go to control panel, runs, and you get rid of that, and then you concentrate on that. So we can see here that this model is not correct because the adopter will be 15 trillions, which is much more than the population in the world. So clearly our first...
Also, there's a tick under the table.
Here, this one.
Yeah. If it maybe untick the previous one, you can see the new one.
No, that's the new one. Oh.
Yes, I mean, if there are more than...
No, it's only one. I think what we can do is that close this and then change the variable contact rate. Let's reduce it to 10. Yes, click that contact rate 10. Say OK, and now change the name of the simulation. Simulation result file name. A smaller contact rate, and then simulate. Yeah. Okay, that's it. Yeah. When you save it in your. Okay. Yes. Now we can see, right? Clearly, the first one is still dominating. Now with 10. We tend to have a better approximation. So untick that one.
Yeah, but right. So, but the scaling stays the same, right? So.
Yes, but in this case, it still show us is still dominating by this. So let's go to control panel. and remove it a smaller time frame.
I'm trying to
just choose it. Yeah. Now we can see. Okay, we are better, but still quite bad in terms of that. Usually, when you have more data, right, you tend to find that make it more specific that process, because you have something where you start. In this case, we are starting to guess this number. But I think, on the other hand, there is a problem here, which is perhaps our theory of what is going on is not complete. We assume that there is a infinite number of users, right? If we close this graph, so when you have a cloud at the end of a flow, that means that there's no restriction. You can have as many numbers as you want. So there's no restriction on the flow. But we know, right, from experience, that there is a finite population who can use Facebook. So perhaps what we are missing here is the other part of the theory, which is what is the pool of potential adopters? No, that could be the missing part of our model. And we can go back to this in a moment, but at this moment, give me back the control, and I'm going to introduce the next part, which is looking at balancing feedback processes. With that, we are going to get into the concept of so the other concept is the goal-seeking structure or balancing feedback loop. And there is a structure, right? The structure basically in the balancing feedback loop, what you have is that there is a goal in the system. And the system, the state of the system tends to change until you reach that goal. So, for example, if we look at the definition of how many people do we want in a company, we have a goal, a desired labor force, and we have the stock of people that works in the company. So basically, a decision maker make a comparison between what you have, what you need, the desired labor, minus what you have, the labor here. And it's a gap, right? It's a shortfall. And that's the same process, the same comparison may happen with the thermostat. This is the desired temperature. This is the temperature in the room. There is a difference, right, in that temperature. That temperature, which we call shortfall, will define the change in the stock, will define the accumulation, the process of accumulation in this system. And this is in this case, is the net hiring rate. It's the number of people that we hire every month in order to achieve this goal. This hiring is not instantaneous. If it were instantaneous, once you have this gap, you fill that goal and that's it. But we are looking at processes that may take time in order to realize. So you usually have some delays in the system, and this is what we call the adjustment time. Adjustment time somehow shows the time that takes for processes to be done. So in this case, even if you need more personnel, it will take perhaps 1 month, 2 months to hire this personnel and change the state of the system, right? Increase the number of people, but then the following month you compare again. You say, I need this number of people, this is my goal, and I have already this. Okay, let's hire this, the difference, right? Let's hire this difference, the labor shortfall, over this period of time, and then we reduce a little bit more the system, and then we compare. That's why we call goal-seeking structure. And it's basically a balancing feedback process, because you see that the change here, right, the labor shortfalls make a higher rate that increases the accumulation, but this accumulation, when it's compared to the goal, tends to decrease the action in the system. And that action tends to decrease until the system is stable. And that's why also it's called a balancing feedback process. So goal-seeking behavior is originated by negative feedback loops that seek balance and equilibrium. The negative feedback loops acts to bring the state of the system in line with the goal or desired state. Sometimes that goal is explicit, like we have in the previous slide, like you have a desired number of people, or sometimes it's implicit. You don't have that, but that balancing feedback process is against a depletion of a certain stock. So, for example, you may reach balancing in a population, right, when the number of deaths drains out all the population. At that point, there is a balancing. There's no more death to happen, but right, it's not a desired goal, but it's implicit in the system. So, in this case, what you see is that sometimes the goals, you can identify the goal, the manager, the stakeholder can tell you about the goal, and sometimes you don't have that. The goal may be a bottleneck in some other resource, in some other stock. Sometimes, and that's part of the discovery of process through the modeling. But one interesting thing, and this is the opposite to an exponential growth or reinforcing feedback process, is that in the reinforcing feedback process, the rate at which the state of the system changes increases as the state of the system increases. In this case, the rate at which the state of the system approaches its goal diminishes as the discrepancy falls. So you can see that the flow, the net hiring rate, will be smaller until the system reaches that goal. On the exponential growth, the flow will tend to be larger because it's not constrained. As the larger is the state of the system, the larger is the flow. In this case, the closer the state of the system to the goal, the smaller is this rate of change until you get an equilibrium. So if we see then the same case that we see associated with entertainment, right? We have Facebook, but we see that this process of equilibrium happens in many markets and in many social processes. And one of these processes very interesting is the sales of video game consoles. So this is the Saturn Nest. This is the first one, right? You see that after a strong growth, they tend to plateau, and you may say, okay, it's because PlayStation comes out and takes some of the customer, but you can see that PlayStation also plateau after a period of time. So here, if you see this type of behavior, the question is, okay, there may be some limit here. There may be some goal implicit in the system. And what can be this goal? Well, basically, this goal is that while you have a number of adopters that talk about the product, right, and they try to, and they convince people who are not using the product to bring here, there's a finite number of people who can buy the product, who can be a user of a product, who can be infected. So this structure tends to be very handy for representing many processes that you see in social system, which is a transfer from a state where it's not with something to a state where it is with something. Either it is a new product, it is a new service, either it is an idea, it is almost any system that you can imagine, at least social. It's this transfer of people with a certain type of behavior into another type of behavior. Sometimes this transfer happens endogenously because the people who are in this state of behavior convince the people who are not in this state of behavior to move. Right, and let's see this equation for a moment. So remember that we have in the previous equation contact rate, right, multiplied by adopters, multiplied by adoption fraction. Right, that adoption fraction, so here is essentially the first part, right, of the equation that we see before, that drives this reinforcing feedback process. Multiply by something very interesting here. So you have here is the chance of finding these people within the total population, this dispersion. So you have here this proportion of that these people may be encountered across these people. So this equation has this part of the equation has a very interesting functionality. One is that this probability of finding these people. And the interesting thing is that this probability is as the potential adopters deplete, because you see that the outflow is coming out, is moving people out of this number of potential adopters tends to become zero as they move into this state. So any people in this state moving on this state will be a point where there's no more people to convince, and that tends to balance the system. So this is here in this case we call market saturation, but it can be any saturation that you see in the system. And you see that this behavior that we see in these systems, right? This in this case arises from two feedback processes. One is a reinforcing feedback process that brings people in, and there is a balancing feedback processes that constrain that growth until they reach this the balance, which in this case the balance is that there is no more potential adopter. So almost all the system dynamics models, you tend to have a combination of these two feedback processes. A reinforcing feedback process driving the system towards exponential change, and a balancing feedback process that tends to constrain that growth and maintain the system in a state of equilibrium, right? This is a very interesting, a very common structure that you see in many social processes. So if you want, I will keep this for a couple of minutes so you update your model, right, with this new structure, and in order to see how will go if we run this simulation again. So let me, before we go to the next stage, which is going into the rules for modeling. Any questions with this part? I'm going to share the screen again so you can update your model and see if you can add a couple of more, add this structure and add a little bit more data and see if now you have better results. So let me share my screen. So I'm going to move this up. So if you have any questions, just let me know. What you need to add to the structure basically is Unfortunately, you have to delete that flow that you have a moment ago, right? You have to delete that adoption rate. This you have to delete because you need to do first the stock of potential adopters and then draw the flow from potential adopters to adopters. Otherwise, the software will not recognize that there is this flow. Can you try to do that? If you have any questions, just let me know, and I will be happy to answer any questions. I will bring back the So, oh, sorry. So first is the structure and then the equation. Anybody has the model updated? So you see that as we develop the model, we usually start with the most simple model that we can think about the problem, and then we add structures as we understand more about the model, more about how it behaves. Maybe through the testing, we realize that it's not enough what we have in terms of structure, and then we add an additional part of the model. We test it, we refine it until we see that what we observe in terms of the model is the behavior that we can see when we look at the reference mode for the model. Any comments? What value should we take as potential adopter? Monique asked. That's a very good question. So let's suppose that the number of potential adopters of Facebook will be half of the population in the world, 3 billion people. So that will be the initial value for the potential adopter, 3 billions. But then we need a new value, right? We need a new value for something else. Is the total population. Let's assume that that is the total population of the world, right? So so that is the number of potential adopters, right? 3 billions. And the total population will be the whole world. I don't know how many we are at this moment, but let's assume that is 7 billions. So if you incorporate those numbers and you have a simulation, it will be very nice to share your screen. And see how does it work, how we are doing with this.
So I could offer to share the screen again.
Okay, that would be great. Just let me stop sharing my screen.
So I went for 8 billion instead of.
Okay, that's good.
Right, so I have 8 billion here.
That's fantastic. Total population, that's good.
And 4 here.
Yes, That's good.
And then I have this here.
Yeah.
But then when I run it, I think my time horizon is currently not long enough because I don't actually get to this like saturation rate.
Yes, and that is this is very interesting because do we know how many people are using Facebook at this point? Now, perhaps 2 billions. Let's suppose 2 billions. Perhaps in this case, what we are sure are the initial values, the values of the stock. We are sure, and this is we have a reference mode that perhaps is the current number of people in using Facebook is 2 billions. So what we may be wrong at this moment is the rate and the other rate. So perhaps we can update that. And give an additional number. So in terms of numbers, so in 2011 it was 900. So yeah. So if we can hit adoption fraction, let's put contact rate. Yeah, that's it. Let's put 7%. And contact rate 20, go back to 20, yeah. Okay, now we see that phase. Yeah, clearly we see now these two phases. If you can expand the graph, so you see that between 2007 until 2014 approximately, you have the trajectory of the reinforcing feedback process. You see that the R was larger than the balancing feedback process. So for 7 years, this is almost an exponential growth. In 2014, now seems to tip off, right? Basically, when you are almost halfway through the process of adoption, now the balancing feedback process becomes stronger. And that's why from 2014 until 2020, you see that the growth tends to reduce, right, until you reach almost that limit. And here there are interesting implications of this simulation. If you are looking, and that's why it's very important, just give me a second before answering that question. That's why it's very important, the time horizon, because if you are looking at this phenomenon from 27 to 2014, and you have data only for that period of time, and you use, for example, a forecasting tool, you will extrapolate this number to perhaps numbers that will be much larger than the ones that you end up, because you don't see that there is this switch on the strength of the feedback process. And so that's why it's quite important many times to have a clear time horizon, because during that time horizon, feedback processes may switch strength and may become dominant. The dominance of the feedback loop may be different. And so that is one important aspect that we have to consider. And in adopters, we see the accumulation, but let's choose the variable for a moment, adoption rate, which shows the flow, the process. So as you can see, this is what's happening every year. So if you see in terms of number of people that are joining Facebook, this is coming from the flow. these are processes. Usually the flows represent the processes, represent the small things that are adding to the accumulation. Sometimes the accumulation cannot give you the right picture, and sometimes you need to go to the flow, but many times you don't have that data from the flow to validate. But through the model, you can infer what will be that data as you are doing in this case. But clearly what is showing here, and this is you can also see in many of the COVID models, is that you have a phase where there's a growth on infections, and then as either there is a lockdown, which means you reduce the potential adopters to a very small number, that curve start decreasing because simply you run out of opportunities. You run out of that stock of people who can get that. And that's also happening in companies, right? You run out of customers for the process. You run out of capacity for attracting. So there's usually this very interesting phenomenon where you have this change in the dominance of feedback loops, and you may not observe in a time series, but you can observe in a model when you simulate over different period of time and you simulate using different values. You can see that how this dominance change and how these changes affect really the final results. Now I'm going to stop for a second to see any of the questions. So Carlos, have you been able to solve your problem? No, just don't stop the sharing your screen. We will. Yes. Green asks, what is the equation for potential adopters? Can you show the equation for potential adopters?
This one here, right?
Yes.
Yeah.
Click, equation. So in potential adopters, because it's an outflow, the variable is subtracting, right? You see at the top that say the name is potential adopter, type is level, then and you say potential adopters, and then in equation you have equal integ. In Benzene language, integ is integral. Is the integral or the integration of the adoption rate over a period of time with an initial value of 4 billion. There is a question from Frederick. I think in adoption rate, you just add the variable adoption from word of mouth. Yes, that's right. And adopters stock, you add the variable adoption rate. Yes. Now, if you have the initial value of adopter 0, yes, that's a very interesting thought experiment, right? You need at least someone who can start that process. So you will never have a product in the market unless you at least give some free samples. You cannot have an epidemic unless you have somebody with the virus. Do you have a question?
Yeah. So yeah, excuse me. So would you normally have an arrow between adoption rate and potential adopters to show that the adoption rate is affecting the stock potential adopters, or it's just implied because it's connected?
No, if you draw your diagram correctly, when you started your flow, right, your rate, you started from inside that box that say potential adopters, you don't need to do anything.
Okay.
And in terms of the diagram, that's a good question. Can we validate the model with that data? Who asked me that question? I lost. here, Azari. You can validate the model if what you are looking is at behavior over time. Maybe your reference mode, which may be coming from expectations, that is good of validating the model without having data. Tomorrow, John Moorcroft is going to show an interesting example of how you validate the model, or you get insights out of a model without having the real data. But in this case, the real data give us a sense of range of expected values for the model. So somehow helps to see that we are on an approximate path of the results that we are seeing. Okay, so let's stop this for this part, and let's go to the presentation. I'm going to go back to my presentation to see. So we look at the two structure, and we can see that most of the models are a combination of these two structure, and that can give you a sense. And by this simple structure, we can see how the feedback loops change dominance and it's basically it's not the structure that change, is the dominance of the structure that changes in the data from adoption rate, in the shape of the variable adoption rate. You can see that at the beginning adoption rate was growing because the dominant feedback loop was the reinforcing feedback loop, but after halfway of the adoption process, the dominant feedback loop became the market saturation feedback loop, and that's why it started declining towards zero. So, and the structure didn't change. What they changed was the dominance of the feedback loop. And this is something that we try to address many times with our models. So let me go. So what are the rules for modeling? So basically, I suggest you that you open the model that I gave you. It's in the share folder, and try to look at that model in the same way that I was showing. So in one hand, you may see my slides. On the other hand, you see the model. So try to go both things in parallel. So this is a model about a bank, right? A very simple model of a bank where you have on one hand the accumulation of customers, right? We call website and phone banking customers. And you have on the other hand the accumulation of staff, right? People who provide support to the customers. It's a very abstract and high-level representation of this company, right? We have something that we call operating policies. So some of these relationships are operating policies. These relationships are decision-making processes that guide the accumulation of stock in using information feedback. So in this case, for example, the accumulation of new customers into this number of customers come from a decision in management decisions of doing investment in marketing. And how do we represent that investment in marketing? By the money that they spend and the efficiency of that investment. So that gives me the new customers for internet banking. Another potential operating policy may be the number of people that we hire. That is a management decision. This is a decision that they make explicitly using the information and using different ways that they consider to run their business. And those different ways, you see that there are information. This is mostly information, the information that they have to make that decision. And then we have the operating constraints. The operating constraints are practical rules for how stocks work and combine to deliver products and services. So in this case, operating constraints, it will be that the ratio between customers and staff will define a certain customer quality, right? A certain quality will be defined by the ratio between the customers and the staff that you have. And this is basic in many service industry. You can have that same situation in a restaurant. You can have the same situation in a bank where if they have very few people in the call center, so every time that you call, there's no enough people to answer that call, so therefore it means that you have to wait a lot of time. Well, that will imply that this company will lose customers due to the service that they provide, right? And how do you measure that? Many times it's a ratio between what is the demand for some service and what is the supply for some service. And that ratio, if it moves in a certain way, will imply that it will generate an outflow especially in the stock, in the accumulation of customers. So we have two things: operating policy, these are decisions, these are discretionary, these are choices, and operating constraints, these are rules that make the business work without necessarily having a direct intervention of a manager. It's like the physics of the business in this case, the operating constraints. These are, we can say, is the social aspects of the business or a system. These are discretionary, these are not discretionary. These happen because of the way that the business works. So when you are thinking about causality in stock and flow models, you have operating policies and you have operating constraints. How do we do this formulation? It's very simple. So new customers, these new customers is marketing expenditure multiplied by new customers per $1 million in marketing. And here is an interesting first lesson of when you use plus or when you use multiplication. These two variables, clearly, if you say that there's more efficiency, you will have more customers. So the sign will be plus. If you have more advertising expenditure, you will have more customers. So both of them, they have a plus, right? This link between these two variables. But when you have a multiplication, the interaction between these two variables has to happen simultaneously. So these two variables are interdependent. If you have marketing expenditure equal to 0, there will not be any effect in this variable, even though you have this effect here. So the multiplication means that these two variables, these effects that are coming from these two variables are interdependent. And this is important when you're thinking in terms of feedback loops. That means that let's suppose that there is a big feedback loop here and another feedback loop here. If this feedback loop is working, but the effect of this variable here means that this will be 0, that may cancel this other feedback loop. So the importance of multiplication means that, or division, like in this case, means that these two variables are interdependent. You need both variables working simultaneously. If you have a relationship that is not interdependent, so maybe you may have advertising and bring new customers, instead of using a multiplication, you use an addition. You may have some process affecting this, while this process may not be present. So that's why it's very important that you, for each pair of variables that are converging in another variable, think, is this process interdependent or they are independent? And when we look to this variable, we say that ratio and customer website staff, we say website and phone banking customers, the more, right, this is positive, the link will be positive. So the more customers that you have, the higher is the ratio. The more staff that you have, the lower will be the ratio. So in this case, that's why you have a division here. This resource reduce this ratio, and but you need both values here in order to calculate that ratio. You cannot calculate that ratio if one of the variables is 0. So that ratio will determine, and this, so we are basically looking at the equation formulation from this perspective. Clearly is that the type of variables that you have, if they are interdependent or they are independent, right? And the type of relationship that you have, which for some variables, this may be a non-linear relationship. And that's what we call estimation of behavioral relations. So this ratio, this calculation that we have here, will be a number. And maybe a number that may be between 30 and 150. So there may be 30 customers for each member for each staff member, or you may have 150 customers for each staff member. If you have 30 customers, like customer losses from internet, this result is a nonlinear relationship. That's why we have the function here of this ratio, right? That's why in Invention we have to do this customer losses function, this behavioral relation, as an additional variable that is called a table. So if you click in this variable in your model, you will see that appear as a lookup variable, but there is a small icon there that if you click as graph, you will see this table there. And this table basically is telling you the operating constraint here, is that this ratio in terms of customer and staff, if you have 30 customers for each member of the staff, you will lose 10% of your customer banking, right, of your customers here. If you have 150 customer per staff, you will lose 60% of your customers at any moment in time. So these nonlinear functions tells you that if you have very few customers per staff, you will lose a small number of customers, but there is a point where if you don't have too higher number of customers per staff, that loss as a percentage of customer increases to a point where losing 60% of the customer is almost losing all the customers that you. So that's the idea of behavioral relationship and using tables. These tables somehow are used as to represent nonlinear functions that maybe they don't have a clear mathematical expression, but you may have some data points that help you to draw these relationships. So at this point, I'm going to stop here and see before we go to the final part of quantitative and see if, based on what you are saying in the model, if you have more questions about that model. Anything that you have seen and you do not understand? From that model?
I do have one question.
Yes.
So we have this arrow which is going from potential adopters to adoption from word of mouth, right?
Yeah.
In the one that we just discussed. So this is only there because I'm using this as a variable in the equation, or why do I need to put this there?
Can you show me what variable do you mean? Sorry.
So yeah, wait a second. So this we have this going from this level to this variable, right? From potential adopters to adoption from word of mouth. We have this arrow, and
Yes.
this indicates that, or this is there because we use this inside this equation, right?
Yes, that's right.
Okay.
That's
okay,
right.
and only if there's an arrow in between, we can use the variables basically in these equations, right? So I couldn't use it. Well, that's a bad example, but I couldn't, for example, use contact rate in the adopters
No.
right now because there's no arrow.
Exactly.
Okay.
But there's one basic principle here, and this is very important. Any accumulation can only be driven by a rate of accumulation. So you need to draw this. You need to draw the flow into the stock to make that level change.
Yes.
You cannot have like adoption from word of mouth directly into adopters.
Okay. Yeah. Sure.
Okay.
Yeah.
This is a basic rule. We want to have very clear of what, because somehow the variable adoption from word of mouth here is an intermediate variable that helps us to keep clean the calculation and seeing all the path, all the causal path that leads to that number in adopter.
Yeah. Okay. Yeah.
Definitely, and if you are coding, if you like coding, you can write a code where you and you will see, I think, in R that all this explanation get a bit lost, because in R you start coding line by line, and that make this relationship a little bit not clear. But when you are using the software, like we are using at this point, Vensim, is that use as many intermediate calculation as possible, because that will help you two things. One is to separate the different causal points in your path, right, between one variable and the other.
Mm-hmm.
And the other thing is that avoid having constant inside the equation, because every constant can be part of a sensitivity analysis. And every constant, every number that you have there, it needs to have a connection with something that is either associated to the theory about the system or associated to an explanation about the system. So in this case, the adoption fraction, we have a meaning for that number. The contact rate, we have a meaning for that number. The total population, we have a meaning. We try to have models that every constant and every equation has some meaning.
Yeah.
Of course, I can imagine that many of you say, why we do all these intermediate steps where I can write the equation directly. But in system dynamics, we try to have the steps very clear in order to have a white box model. So a model that if you show to somebody who are not you, you can understand it.
Yeah. Okay. Thank you.
No, you're welcome. There are some questions. I'm going to upload, yes, definitely, the models now. Yes, definitely. That's I'm going to upload it now that the models that you are asking, absolutely there is no problem. So now you will have in your in the share folder the Facebook case for you to look at that. So I have some questions. Athari say, can we populate the model with the very large data using this version of the software? What part of the model do you want to populate with very large data? Because as you can see, our models tends to be very compact in terms of the data, the stocks. But the stock, you only need one data point, which is the initial value. The rest of the trajectory of the stock is calculated every delta time by just simply adding what is coming from the flow. So that's why we say that it's endogenous. So all the equations tends to fit itself to make that trajectory that you see in the software. I uploaded the Facebook exercise for you. Any other questions from the Bank of Granite website? So the last 30 minutes is mostly as a discussion and reflection. So it will be good if unless you want me to show you a more complex model, or at least parts of that model, or I'm happy to answer questions for you to understand better this exercise. So let me know if you have more questions about these two exercises. So data, definitely. What we said is that you can have a time series like we have in Facebook to be able to calibrate the trajectory of our variable that we want to look. And in this case, in Facebook was the number of adopters, the number of customers. That was our key variable, and we have an accumulation of that we wanted to see that more or less follows that trend. In this exercise, we didn't have the real data for the contact rate or the adoption fraction. So therefore, you need to do an exploration here, some testing, adapting, until you see the results. But we saw that clearly any change in those values will not give us the necessary precision to what is the trajectory of Facebook. Why? Because the theory that we were using to develop that model was incomplete. Why was incomplete? Because we were missing one important constraint on the growth of Facebook, which is the finite number of users. So therefore, we learn more about the system, and we added an extra part to the model. You see that we learn more from our own mistakes on defining the boundary of the system. We go back to the model, we incorporate that part, we run, and we see what we have in terms of results. We see still not quite good. We look at the constants. We change the constant until we have a result that we feel provides a good approximation to the trajectory that we see in Facebook. We have that, right? That is the last part, which is the testing, the calibration of the model. And then we go to the next step, which is the policy formulation and experimentation. And we experiment with that. We clearly look at the different graph, right? How the feedback processes switch. The dominance of the feedback loop changes. At the beginning, the dominant feedback loop was a reinforcing feedback loop. And then in the later stages, the dominance of the feedback loop, of the balancing feedback loop was stronger. So when you look how do you see those changes in dominance? Either looking at the graph of the behavior over time of the variables because they change their trajectory, or usually when you capture most of those changes in the dominance are in the flows. The flow is usually those variables when you see that very clear. And that's why it's always, once you have the model and you start having the first results, go and each of the variables and look the different trajectories. That will help you to infer, right? How is this changing in terms of dominance of the feedback loop? If you want to be sure what feedback loop is working, you can use the tools, right, on the left-hand side, where I click on what is the feedback loop that is going into that variable, or click on the uses or on the causes tree. And so for each, and that's why we want to have all the steps, intermediate steps, clearly defined in the model, where you can trace all the causality in order to explain what you are saying in the model. That is the basic process that you do on system dynamics models. You start with the theory, you start with an understanding, you start developing the model, you test the most simple model, you add more structure, and you keep testing until you have a model that is basically reflecting what you want to represent from the problem. Is that more or less clear? This is the most important message that you need to have for today. Is that more or less clear? So, okay, excellent. So I can go very quickly to one of the models that I did. It's part of the presentation. Sort of moving to the next step, right? In terms of questions about the model. This is a model about a human resources in a professional service company. I am not going to go in detail into that model, but the interesting thing is that this model, and this is another thing that you will learn, is that there is usually common structures that you can use for starting your model. And in this case, in system dynamics, there is a common structure called aging chain. And how is this structure? It's basically, this structure tends to apply to any company. You hire people with the novice conditions. It may be in a university, that will be a lecture. Through training or by time, becomes intermediate staff or becomes senior lecturer, then is promoted to the next step, which is called advanced staff, and that or in a university reader, promotion to a senior level, become professor, and then become something else. In a professional service firm, is the novice, intermediate staff, advanced staff, senior staff, managers. That tends to be a very common process. If you see in terms of population, people, young people, 0 to 5 years old, 5 to 10 years old, 10 to 15 years old, 15 to 20 years old, 20 to 25 years old. It's the same structure. And these flows is moved by usually age, or in this case training, but there is a rate that is depending on this flow and move to the next step. What can happen to people in each of these states? They can go out from the system, right? They can leave, right? They can leave and go to other companies. They can die if you're thinking about population. But this structure tends to be very common in most cases where you need to show one group of entities, people, can be skills moving across different stages, can be customers. And usually what you do in that is that each of these components, they have different either numbers, or they have different characteristics, or they have different abilities. Right? With those abilities, the combination of these abilities can help you to do something. That's is what we call here times in analysis states. That is the capacity that you have. So a number of projects that they can cope with this capacity that they have, and the number of projects that they have, and the number of projects that they may have in the future. So with this structure, you can generate, for example, abilities to do things. You can generate, if you are in a population model level, you can calculate demands for healthcare. You can calculate demands for services, because you attach to each of these stocks some characteristics, and that's what you do in the model. So what's happened with these stocks is that over time they change, right? These rates, they tend to move it to make this change. And what's happened is that if you have in a certain situation where some things happen, is that these changes in qualities, right, of these people will have an impact on the quantity that the the skills that they have in terms of activities. So you can see that depending on these conditions, they will have more time to do some things and less time to do other things. So that's why you have these oscillations. Oscillations are also coming from balancing feedback process, right? Because in this case, these people try to do that some projects, but they have to reduce doing these projects up to a point that they need to do more of this. So there is a pressure to do more of that, and they stop doing these processes. So usually in this type of chains, you see oscillations in the demands, because the demands from this, for example, will be different than the demand of that. And as things progresses through here, you have different a set of conditions for that. So based on that, you can create I created a model where I try to show these adjustments that you see in previously in terms of balancing processes between you have a demand of time, you have a supply of time, and there are short-term adjustments. These are the short-term adjustments. And what you try to do with this, usually this project, is to look at the long-term adjustments. And the long-term adjustment means to look at what you need to do here in order to have the necessary things here. If you're thinking in terms of aging population, right, what do you need to do with these different categories that are aging in order not to make perhaps having too much demand of healthcare services at this age? So perhaps you start giving more healthy and better lifestyles, so in order to have at this stage people who are in very good condition, so they don't need to be a lot of time in the hospital. So this same structure that I'm showing here, you can extrapolate and use in many similar projects, where you have usually short-term adjustment, balancing feedback process between a demand and a supply. But usually what you try to do with system dynamics is these long-term adjustments that make the supply match that demand over time. So this is an interesting project, and this I wanted to show you some as a way of how you progress with a little bit more complex structure over time. So with that as an introduction of Steve from this perspective, I think we are fine. There are some documentation of system dynamics models that it will be good that you look a little bit more for how you present models. And in terms of the papers that I show in this today, the first causal loop diagram that I show about the wine bars is in this journal. So I have a page in Google Scholar, so you can look for this paper, and if you cannot download it, I'm happy to send it to you. The paper of the business, where you have all this number of feedback loops and how you calculate structural complexity, you can see in this paper. And the last paper that I show you about the structure of a professional of a firm with novice staff to manager can be seen in this paper. So these papers explain these models in more detail. I'm happy to give it to you if you cannot have access to them. For today, I think we cover a good amount of concepts. I think if you are on that idea that you start from understanding the problem clearly in terms of relationships, translating that into a set of causal loop diagrams, and may stop there for your purpose. If you go to the next step, start thinking about accumulations, how to drive this accumulation through flows, and starting to understand the operating policy as a structure, and then the behavioral relationships. I think if you understand those pretty clear, and I will show you that at the end of the course, you can interpret any paper that you see that has been published with a system dynamics model. Those are basic principles applied in any research in SD. So before we leave for today, is there any questions? Anything? Just to, okay, Moritz.
So I have one question. So I'm from Kühne Logistics University in Hamburg, and I'm just starting to get into system dynamics, but we are using a different software. It's called PowerSim. I don't know if you've heard of it. And I was wondering if there are any advantages or disadvantages using this software or using VenSim that you're aware of.
No, not really. Not really. It's the good thing about system dynamic software is that all of them use the same structure. So in all of them you will find the stocks, flows, auxiliaries, and table functions. What may differ between different software, the version that we are using in VenSim is for learning purposes. So, but if you go to a professional version in VenSim, you will have optimization engines and more sort of Monte Carlo simulation. And the other software, they also have that. I think PowerSim, I think. So most of them have functionalities. They are very minor differences from my perspective.
Okay. And obviously my professor knows the other software, so I will obviously stick with
that. That happens a lot. That's why I show you the three software, and that's why during this course we will see 3 different software, so you have a feeling for the 3 different software. And you can see that each of us have different preferences. But if you understand the principles that a box will be always an accumulation, you have the rate of accumulation, there are feedback processes, no matter what software, it's a question of preference, but the principles are the same.
Okay, perfect.
Thank you for the question. Any other questions? No questions. Okay. So you have all the models in the share folder. Please take a look at this. Happy to answer any questions if you put it in the chat later on. And yeah, perhaps it's too much to absorb and you are already very tired after a long day. But yeah, you know, every professor tries to give as much as they can. So apologies for that. Tomorrow you will have a more engaging day, very relaxed with John. Is very good in his explanation, and as he takes system dynamics as a storytelling, so you will see his way of explaining models and how you represent things. So he will be a very good, and you will learn another software. So before we finish, how many of you did the tutorial? And how many of you feel confident after the tutorial that you understand the basic functionalities of Vensim? Can you raise your hand, please? Not even strength to raise your hand, or you didn't do the tutorial? Okay. No. Okay. It's very important that you do the tutorial too. Okay, Carlos said he did the tutorial, but it could be good if there are some handouts of other exercises. Yeah, we can put it at the end. Okay. So thank you very much for being up to this time. See you tomorrow with John. Thank you. Take care.
Bye.
Thank you. Bye.
Bye-bye.
Thank you.
Bye. Sure, if you have a question.